Alright, we're back with a high-pitched whine of the projector. Sorry you have to listen to that again. We are going to talk today about electricity, and specifically electrostatics. You did this last year. You actually did more work last year than we're going to do this year, so hopefully this should be a review. We are not going to talk about electric fields in this class. We are not going to talk about electric potential unless we are talking about circuits. That's two things that you do not have to know for this class. We are going to be focusing on the nature of electric charge, methods of charging things, including polarization. Well, that polarization isn't a method of charging, but we're going to talk about polarization and methods of charging objects. We are going to talk about, all that applies to electroscopes, which you did a lab on last year. And finally, we're going to talk about electrostatic force. My intention with this is to have you guys watch this weekend, okay? This upcoming weekend. It's, what is today? It's March 13th, Pi Day tomorrow, 3/14. My intention is for you to watch this weekend, the notes here, and also the tutorial. And then, let's see, so Friday. On Thursday of next week, having a test on electrostatics. It will be a very short test. I am not going to really talk about electrostatics in class. I need to get started on talking about circuits because circuits is harder than what you did last year, okay? So my intention for this is to be a quick review of electrostatics. You will do 3 homeworks. I will give them to you, Monday, Tuesday, Wednesday. Or no, I'll give them to you all over the weekend so you can work on them if you want. It's going to be 2 multiple choice, 1 for your response. Should be very short, and hopefully last year they did very, very well in the electrostatics test. That's my intention for this time. Sorry if you hear the music, there baseball practice is going on. So, to start off, we have to talk about electric charge. Electric charge it's hard to describe, it's like mass. Why do objects have mass? They just do. Why do objects have electric charge? They just do, okay? Electric charge is a property that objects can have, and there are a couple different types of electric charge. So we could say that objects can be positively charged, such as a proton. They could be negatively charged, such as an electron. Or they could be neutral, which I guess I'll symbolize with a 0. And obviously, neutral is a neutron. So those are the different types of charge. You can either have charge or not, and if you have charge, the object can either be positively or negatively charged. The units. Well, there's kind of a couple of units for this. 1 unit of electric charge is the coulomb, named after some guy named Coulomb, symbolized with a capital C. You can also talk about electric charges in terms of the charges themselves. Okay? You can also talk about what are called elementary charges. The symbol for elementary charges would be like 1e, or I guess just e. 1e would mean it's 1 elementary charge. And the relationship between the two, because sometimes we talk about coulombs, we have a lot of charges. Sometimes if we don't have a lot of charge, we talk about elementary charges. So the relationship between the two. 1e is equal to either, well, I guess I should say plus or minus 1e. It could be positive or negative elementary charge is equal to either positive or negative 1.6 times 10 to the negative 19th coulombs. Okay, so 1 elementary charge is a very small fraction of a coulomb. A coulomb is a lot of charge put together in one place. If you want the reverse, what is 1 coulomb equal to? It is equal to 6.25 times 10 to the 18th e's. Elementary charges. Okay? And I guess I'll kind of fit in on the side. This is a scalar quantity. It is not direction based. Okay? You don't have charge north. You just have an amount of charge. It's like mass. Okay? Now, we talked, usually when we talk about electric charge, we're talking about an object being positively or negatively charged. That's not the case for most objects. Most objects are neutral. And it's not because they don't have any charge. It's because they have equal numbers of positive and negative charges. Okay? So really what that boils down to is they have equal numbers of protons and electrons. Equal numbers of protons and electrons. Great. We're going to have two more lines to fit down here. Just as far as the nature of a proton and an electron go, electrons can move. If you remember your chemistry, electrons are located outside of the nucleus. They're in electron orbits or shells around the nucleus. So electrons can move. And your examples of this, obviously, are ionization. They move in terms of energy levels. Unfortunately, not something we talk about this year, one of my favorite topics in physics. And also, obviously, current. Well, you have electrons moving. However, protons, they are in the nucleus. Unless you somehow just have a rogue proton that's tunneled its way out of the nucleus, can happen, but very rare. We're not going to talk about it. Protons are pretty much stuck in place. Okay, they're kind of locked in place. Protons are stuck in the nucleus. It's the electrons that move around, and that's going to be important when we talk about charging. The last thing that I want to talk about in terms of just general electric charge stuff is that we have something called quantization of charge. When you hear the word quantization, or quantize, or quantum, it sounds really scary and like very, very advanced scientifically. It's not. All quantization means is that something comes in a set amount. It is discrete. Okay? There's not a continuous amount of this thing. And what that means is, well, let me just keep writing, and I'll become a little bit more clear. There is no charge smaller than an elementary charge. That's why it's called elementary. Now, for your Regents kids who last year, you're saying, but what about quarks? We're going to ignore quarks for right now. We're not talking about modern physics. We only really discovered quarks about 50 years ago. We're not talking about quarks, okay? We're saying that charge is quantized, okay? There is a set amount of charge, there's a smallest amount of charge you can have. It's equal to an elementary charge, which is equal to this amount. You cannot have smaller than that for an amount of charge. It is impossible, okay? It does not exist. So, you cannot have, I guess I'll switch this up, 1.6 times 10 negative 19 C. So what this means is you could not have 0.8 times 10 to the negative 19th C, or coulombs, for a charge for an object. That would be like half of a proton or half an electron. Those things don't exist. Okay? You can't have half of an electron. You can't have half of a proton in terms of charge. It doesn't exist like that. Another way you might see this, you might see no fractional charge. So you couldn't have, and this is kind of related to what I was saying, you couldn't have like 1/4 of an elementary charge. Or you couldn't have like 2.4 times 10 to the negative 19th coulombs of charge. Why can't you have this? It's greater than 1.6 times 10 to the negative 19th C. It is, but this would imply that you have 3/2 or 1.5 elementary charges. So charge has to be a multiple of this. Okay, it has to be a multiple of this. Or I guess, in other words, of saying you must have a whole number of elementary charges. No such thing as a fractional number of elementary charges. On to attraction and repulsion. Really quick, for attraction and repulsion, you knew this probably back in elementary school, probably maybe even earlier. It's similar to magnets. If you have like charges, they will repel. You have opposite charges, they will attract. That's pretty obvious. Like charges repel, opposite charges attract. The more difficult one to remember for most people is what happens when you have a neutral object and a charged object. Okay? Neutral and charged. And for this one, I want you to think about what happens when you take a balloon and you rub it on a sweatshirt or something, and you put it next to your hair on a dry winter day, okay? What happens? Your hair stands up, right? Now, the balloon itself, we have charged it by rubbing, by friction, okay? The balloon is charged. You yourself, however, you are not charged. Humans are typically neutral, okay? You do not have an electric charge. But what happens to your hair? It still attracts to the balloon. If your hair is attracting to the balloon, then that means that you, a neutral object, are attracted to the balloon, a charged object. So when you have a neutral object and a charged object, they attract. They do attract. And then finally, kind of obviously, if you have two neutral objects, neutral and neutral, they do nothing. Okay, so there's a few minutes about just the basics of electrostatics, okay? What electric charge is, it's a property some things have. Units are coulombs or elementary charges. You can have positive, negative, or neutral. Most objects are neutral because they have equal numbers of protons and electrons. The electrons are the ones that can move, protons are kind of locked in place, and charge is quantized, okay? Charge comes in multiples of elementary charges, whole number multiples. Cannot have a fractional amount of charge. You cannot have a fraction of an elementary charge. It's easy to see for elementary charges, a lot harder to see for charge when we're talking about in coulombs. In order to tell if you have a fractional amount of charge, take whatever the charge is, divide it by 1.6 times 10 to the negative 19th coulombs. If it comes out to a whole number, you're good. If it comes out to a non-whole number, then you did something wrong and you've got fractional charge. Not good, no good. We're going to go and talk about polarization now as a lead-in to talking about some of the different methods of charging. Okay, so the definition of polarization. Okay, I should be able to get both of these done. Definition of polarization. Definition is the movement of charges inside an object due to an external charge. Okay. Polarization is something that happens to every object, happens to all objects, but it works best with conductors. This is our first mention of conductors. Okay, we're not going to talk too much about them. The best way to describe a conductor is, and I'll do this off to the side real quick, we'll talk about conductors and insulators before we get back to polarization. A conductor is an object in which the charges, electric charges, in other words electrons, can move between atoms easily. Most obvious example of a good conductor is metals, okay? That's the whole point of why we use metal wires. Metal allows the electrons to move very easily throughout the wire. Okay, so metal is our example of a conductor. There are other good conductors as well, like water. Metal maintains a very loose grasp on the valence electrons, so they're able to flow very, very easily. Okay, let's see here. In a conductor, charges always tend to spread out. So, I guess, in a conductor, if the net charge is not zero, then what happens is the charges tend to spread out to be as far away from each other as possible. Charges tend to spread out to be as far away from each other as possible in a conductor. If it has excess charge, if it has a net charge one way or another, whether it's a positive net charge or a negative net charge, the charges will spread out to be as far away from each other as they can be. Really what this means, and this is something you should remember because it comes up on homework every once in a while, is that the charges go to the surface. And they spread themselves out on the surface so that they are more or less equidistant from each other. It's kind of neat, okay? The charges just, it's not that they know to do that, but they find the spot where they are as far away from other charges as possible, okay? They find that niche and they stay there. That's what a conductor does. They allow charges to move around easily. If there's a net charge on a conductor, the charges go to the surface and they spread out. On the other hand, instead of a conductor, we could also have something called an insulator. In an insulator, charges cannot move between different atoms. Even though they can't move, polarization still occurs.